Hi, in this talk I'm presenting a joint work with Nicolas Resch for ITCS 2026. As you can see, the title of our work is quite a mouthful, so I'd like to start by just parsing that title, explaining all the technical terms in it, which will hopefully make you appreciate the result that we prove in this work. Afterwards, I'll explain a bit more about how we proved what we did. So the title of our work is Linear Time Encodable Binary Code Achieving GV Bound with Linear Time Encodable Dual Achieving GV Bound. So we're claiming in this work to construct something called a binary code, which has the property of linear time encodability as well as the property of achieving the GV bound. I will explain what all of that means in a minute. In addition, we're claiming this binary code has something called a dual, which is another binary code, and this dual also has the two properties of linear time encodability and achieving the GV bound. Finally, implicit in this title is the fact that this binary code and its dual are what's called linear, where linearity here means something different from linear time encodability. So let's take the title and go through these terms one by one, starting with the binary code. To explain what a binary code is, it's easiest to explain first the problem that a binary code attempts to solve, which is the problem of communicating over a noisy channel. Let's imagine we have a bit string of length k, and we want to send this bit string to somebody over a channel, but this channel has the property that it can flip some fraction of our bits, maybe 1% or 10%. Clearly, if we have agreed upon that we can send any length k bit string, if any one of the bits flip, we receive another length k bit string, and so we won't be able to tell that errors occurred, let alone correct them. One way to visualize is to see all of our length k bit strings, all of our messages drawn out in this space as points. Maybe we want to send this particular bit string m, but a bit flip now is represented by moving across this space to another point. The distance here represents the number of bit flips, and since all of these points are valid messages, if an error occurs, we have no way of detecting that. The way a binary code solves this problem is by mapping the messages to a much larger space before sending them. In this example, instead of sending the length k bit string m, we might send instead the longer length n bit string, which we now represent by c, the output of some encoding function of the original message m. If now an error occurs again to our encoded message, we again can view that as moving a little bit inside of this space, but now we don't necessarily end up with another valid message or valid encoded message. Instead, we are much more likely to end up with a bit string which is not agreed as a valid encoded message, which immediately tells us that an error has occurred. Moreover, if we can guarantee that the distance, meaning the number of bit flips between any of our valid encoded messages, is at least d, then we actually have the property that if at most, in fact strictly less than d over 2 errors occurred, we can always correct the errors and recover the original message. And this is seen quite easily from this diagram. We can imagine drawing a circle of radius d over 2 around our encoded message, and as long as less than d over 2 bit flips occur, we're inside of this circle. When the distance is in fact d, this circle doesn't overlap with the circle around any other encoded message, which means that by just finding the closest encoded message to the received bit string, we can guaranteed find the original message. Usually when we talk about a binary code, we refer to it with the letter C, and C refers to the set of all encoded messages. So we do not explicitly denote the encoding function or the decoding function, where the decoding function maps a bit string to the nearest encoded message. This presents a trade-off between the size of a code and the distance. We want the size of our code to be as small as possible, which means that n, the length of the encoded messages or code words, is small. But obviously, if you make the size smaller, you're pushing the code words closer together, which decreases the distance. The main question we can ask about a code is therefore, what is the optimal trade-off between size and distance? This is where we get to the second term, which is the GV bound, or as we write it out, the Gilbert-Varchamov bound. This bound presents the best known trade-off between size and distance for binary codes. The way we can prove the Gilbert-Varchamov bound is actually quite simple. Originally, this was conceived of by Gilbert simply by greedily sampling random points. This ends up giving you this best known distance size trade-off at the cost of exponential randomness, space, as well as time to sample this code, and also exponential time to encode or decode this code, making it quite impractical. This is where we get to our next term, which is linear. A code is linear if it is a linear subspace. We think of all the bit strings as vectors, and so a linear subspace in the case of binary simply means that this set of vectors is closed under addition, mod 2. Another way of saying this is to say that the encoding function can be represented as a matrix. What Varchamov showed is that if you take a random linear code, which is simply a random matrix, this also achieves this best known trade-off between size and distance for binary codes. But as you can see, this only takes quadratic randomness, quadratic space, and also gives you quadratic encoding time for your code, because you can simply use the matrix, a matrix vector product for the encoding. This is obviously much better than the idea by Gilbert in terms of the amount of complexity. But one can go even further and demand that the encoding time is not just quadratic, but in fact linear. This is not just useful in error correction, but as the theory of error correcting codes developed, codes have been applied in many other areas of theory, including in cryptography. And especially in cryptography, having a code be extremely efficient, which basically means a linear time, because you can't really go below that, becomes very important. One example is interactive proof systems. These are systems where you have a powerful verifier trying to convince a powerful prover trying to convince a verifier of some fact. In many such instances of proof systems, codes are used to encode the communication between these parties. And often the encoding time of the code becomes the dominant time complexity in such a setup. Finally, when you have a linear code, the dual of that code is simply the orthogonal complement of it. That is, it's the set of vectors which are orthogonal to all the vectors in the code. In our example, where we have a length k bit string mapping to a length n, mapping to code words of length n, we have a k-dimensional original code. The orthogonal complement would be n minus k dimensional. The dual of a code might seem quite arbitrary, but in fact, in applications of codes, again, especially in cryptography, the dual is often instrumental. One example is in secret sharing, where one takes a secret, for example a bit, and attempts to share it between a number of parties, such that only enough of the parties can recombine their partial secrets to recover the original secret. The security of such schemes is often reliant on good distance of the dual code of some code used in the construction. In other words, very efficient codes, meaning linear time encodable, as well as having good dual distance, are often key properties in the applications of codes to cryptography. Which is why we had the question, can we find a pair of binary codes which both have the best distance you can hope to achieve with binary codes, namely the GV bound, but which also are very efficient to encode, namely linear time encodable, and in particular linear time encodable with very low constants as well. In other words, we wanted to construct a fast good code with a fast good dual. We didn't have a specific application in mind, but we would imagine that such an object would find interesting applications in theory in general, but in cryptography in particular. To drive that final point home, we want to briefly highlight a potential application of our codes. This is the application of the encrypted matrix vector product, as studied in a recent work. This attempts to solve the following problem. You want to compute matrix vector products, but the matrix vector product is too complex to solve on your own device because the matrix is very, very large. So you want to offload this computation to another server. However, you don't trust this server completely, and so you won't want this server to not learn anything about your matrix nor about the vectors which you're using. The way the authors propose we can solve this problem is as follows. You take your matrix and encrypt it with some secret key S. You can then forget the original matrix. You send the encryption to the server. Subsequently, all the vectors which you would like to compute the matrix vector product of, you encrypt also, and you send the encryptions to the server. The encryption procedure uses a binary code, and it has the requirement that the code as well as its dual have good distance. The better the distance, the better the security. The server in this setup learns nothing about the original matrix nor the original vectors. And the server outputs a value from which you can rediscover the matrix vector product in a time that's roughly proportional to the encoding time of the code. And interestingly, the key can be reused indefinitely. Now, the authors use a code for this which has a quasi-linear encoding time. One can see that by using our codes, you can improve this to linear time. And as I mentioned, very low constants as well. Unfortunately, there's two caveats to showing that our codes can be used for this specific application, which we didn't yet prove, as we gave this example more as a proof of concept. One is that the decoding of the code has to be hard, which we certainly expect to be true but haven't proven. Moreover, we require giving the code in a so-called systematic encoding, which I won't go into here, but which we also didn't prove. So, hopefully this has motivated to you that a fast good code with a fast good tool is an interesting, or a pair of interesting objects. I'll now say a little bit about how we constructed this object. We started from an existing fast good code. Remember, this is all for bit string, so binary. These are the so-called repeat, accumulate codes. Let me explain how these work. These have a very fast encoding time, which we can see from the encoding procedure, just 2 times n-1 XOR gates. To start off, you take your message, which let's say is length k, and we repeat it some integer number of times. The integer can be chosen to be whatever you want. It's just there to make a bigger space, which you need for error correction. The bigger the space, the better the distance. You take the repeated message and you randomly permute it. You then apply the accumulation operation, which is very simple. For bit I in the output, the way you compute it is to take the sum of all the preceding bits in the input. So bit I in the output becomes the XOR of bits 1, 2, all the way up to bit I in the input. Let's quickly run through an example. Let's say we have this message 010100. We repeat it 3 times in this example. We permute the string randomly, and then we apply the accumulation. Now for the first bit, accumulation is just copying the bit over. For the second bit, we take the XOR of the first bit and the second bit. For the third bit, we take the XOR of the first bit, the second bit, and the third bit. Now as you can see, this ends up just copying the first bit until you read another 1 in the input vector. That's where you start outputting zeros. Until you read a 1 again in your input vector, or you have another kind of state change and start outputting ones again, and the procedure continues like that. You can see from this example that you just need 2 times n minus 1 XOR gates to implement this. What might not be obvious is that this code is linear. One can see this by observing that both repetition, permutation, and accumulation are all easily expressed by a matrix. And linear codes have a very useful property, namely that the minimum distance between any pair of code words is in fact equivalent to the minimum weight of any code word, where weight refers to the number of ones in your bit string. This makes the analysis of these codes much simpler. Instead of having to analyze every pair of code words to find the 2 code words with the shortest distance between them, we can get away with just analyzing each individual code word and finding the one with the fewest number of ones in it. The question of why is this a good code then becomes, why does this operation give us an increase in the weight of the messages that we put in? This is where a simple fact comes in, which is easy to prove. When you accumulate a random length and bit string of a fixed weight A, the output weight that you expect is always n over 2. In other words, you always expect half the bits to be 1, even if the vector that you put in has weight 1, 2, or some other constant. This is exactly what we want. All the low weight messages that we start with will shoot up to a much higher weight through this operation, at least in expectation. At a very high level, the way this code then works is that the repetition makes the space much bigger, and the permute plus accumulate operations slowly increase your weight and thus distance. So why do we do exactly 2 rounds of permute accumulate? Well, as Ravazzi and Fagnani showed, as you add more of these permute plus accumulate rounds, the distance that you expect to obtain converges exactly to this GV bound, the best known distance that you can get for a binary code. And they show that if you do 2 rounds, you're already very, very close, whereas with 1 round, you're all still very, very far off. Now, the caveat here is that the code only attains this distance with a certain probability, where the probability is over the choice of the permutations. To work out whether you have any decent shot at a good code, what authors did is analyze the expected number of low-weight code words, which, by Markov's inequality, is a direct upper bound on the error probability, where this is the error probability of sampling a code which isn't good, which doesn't get close to this GV bound. The reason this is easy to analyze is because the permute plus accumulate operation admits a very easy expression for the probability that it maps some weight A to some output weight B, which allows you to express this expectation very easily. So this is the RAA code, which is fast and good. Unfortunately, it's easy to show that its dual is definitely not good. It has very bad constant distance. So what we try to do is take this code and turn it into a code which does have a good dual. The way we did that is by adding another operation, which is in fact the inverse of the accumulator. The way this operation works is simply by accumulating only the last 2 bits. So if you're trying to find out what the bit I in the output is, well, it's not the XOR of all the preceding bits, but it's just the XOR of the last 2 bits. This can be seen as accumulation in the dual. Applying this operation has the same effect as running an accumulator in the dual, and therefore improves the weight and therefore the distance of the dual code. So the codes that we end up with aren't RAA for any number of rounds, but rather RAD AD, repeat as long as you want, and RDA, DA, etc. This pair of codes can very easily be shown to be dual to one another. The observation here is that if you apply AD, that's actually equal to DA, and that's equal to the identity matrix. Both codes are still very fast to implement. We already saw that applying the accumulation operation is very simple, requiring just n-1 XOR gates, and the same is true of the D operation. To analyze these codes, we took the same approach as for the repeat, accumulate codes. We analyzed the expected number of low-weight code words, which again, by Markov's inequality, is the direct upper bound on the error probability, the probability that you sample permutations generating a bad code. Now the challenge here is that while the accumulator is known to increase the weight in your current code, and D increases the weight in your dual code, applying the D matrix in your current code can actually decrease the weight very much. You can go from a vector with a very high weight to a vector of weight 1, which is something that cannot happen under the accumulator. We had to carefully analyze that the D matrix doesn't do this too much, and that it balances out with the accumulator to still give you good distance. Fortunately, we end up doing this, and our conclusion is the following. This pair of codes, RAD, RAD, etc., and RDA, DA, etc., are, as I said, a pair of dual binary codes with linear time encoding with very low constants. And this is the most important part, which took the longest to prove. They both have distance which converge to the GV bound with the number of rounds, where rounds refers to applying permute, then A, then permute, then D, and the dual of that. We require 3 rounds before the code is good at all, where good means that the distance is linear in the length of your vectors. But with these 3 rounds, you're already very close to the GV bound itself. That was our talk. Thank you for listening.